Hello everyone, I'm Li Yanzhen from Tsinghua University. It's my pleasure to present our work here. This is a collaborative work from Tsinghua University and the University of Sydney. In this work, we present Vapro, which is a virus profiler that can detect and diagnose viruses even without source code of applications. Users of large-scale supercomputer systems may have such experience that programs have various performance for multiple executions, even on the same computing nodes. In this example, we run a parallel program for 100 times on the same nodes of the Tianhe 2A supercomputer. The vertical axis of this figure shows their execution time in seconds. We can see that the worst case is 1.7 times slower than the best one. This phenomenon is caused by system variance. As a result, programs can become slow and unstable. A slower program consumes more resources to complete the same job, and the unstable performance makes it very difficult to understand the program's behavior. Users would often ask themselves, is my program running on the same bad nodes? Can I optimize my program to avoid variance, and can I get a better performance by resubmission? To answer all of these questions, we need to know when, where, and more importantly, why system performance variance happens at runtime. The existing approaches for this problem can be classified as three classes. Benchmark is an easy method to detect variance, but it's intrusive to system and generates extra variance. The second kind of approach is profiling and tracing. They are widely used but requires lots of expert efforts to detect and diagnose variance. The third method is based on static analysis. It can automatically detect variance, but it requires the source code of applications. These conditions are often not satisfied in a production environment. What's worse is that it cannot diagnose variance. Now, we can say that an ideal variance profiler should satisfy the following conditions. It should work without source code, it can diagnose variance, and be automatic. Our work is focusing on how to detect and diagnose variance without source code. Vapro is based on an important observation about fixed workload fragments. Fixed workload fragment is a fragment of program execution with same workload. With workload, we can divide it by time to get performance. For example, we have three fixed workload fragments, but they have different execution times. The fragment with a short time has better performance, and a long time one has a bad performance. This can be a detected variance. So fixed workload fragments can be naturally benchmarked inside programs. And the key idea of Vapro is built on fixed workload fragments. Vapro tries to identify fixed workload fragments without the source code of applications and then leverages them for variance detection and diagnosis. Next, let's come to the workflow of Vapro. The first step is finding fixed workload fragments. For an execution of program, we want to slice it into fragments. Then, with the binary-only identification method, we can identify fixed workload fragments in the execution. The red blocks and the blue blocks represent two classes of fixed workload fragments. Based on the fixed workload fragments, we can calculate their performance and detect variance. Finally, we have known when and where variance happens, but there are many reasons for variance, including hardware reasons, such as processors, memory, disks, and networks, and software reasons, such as operating system. To locate the reasons of variance, we propose a variance breakdown model. Based on it, the variance is broken down into different sources. Now, we are going to the details of how Vapro works. At first, Vapro collects fragments from the program executions. A fragment is an execution of a code snippet. There are three types of fragments. There are computation, communication, and I/O fragments. Vapro split a program execution by external function calls. For example, communications such as MPSN and receive, and I/O operations such as read and write, and threading operations are all external functions. Vapro intercepts external functions with dynamic linker at runtime. For example, the left code snippet has two communication operations, send and receive, and there are two different computations among them. Vapro will get two sets of communication fragments and one set of computation fragments for this snippet. However, the problem is that fragments with different workload are mixed together. We have to differentiate according to their workload. To realize this, we should represent workload at first, although only binaries are available. We discussed the computation workload at first. The matrix measuring workload should remain stable on the noises. We choose PMU matrix to represent computation workload. Among hundreds of PMU metrics, total number of instructions is an ideal metric, since it is related to workload. More importantly, it only counts the instructions of application processes but not other noises. In this figure, we show the execution time and the total number of instructions of fixed workload fragments on the computation and memory noises. In both figures, their execution time, that's red circles, vary a lot, but the blue blocks is stable. That's the total number of instructions. This is desired since workload should not be influenced by variance. We can also select more such metrics, such as the number of load and store instructions and that of branch instructions. Now, let's move to the communication and I/O fragments. Their behavior is different from computation. This figure shows the performance data of repeated execution of fixed workload communication fragments. In this figure, not only the execution time, but also the total number of instructions vary a lot. The PMU metrics are inconsistent with communication workload for many reasons. For example, there might be busy waiting in communication to deal with dependence. To solve this problem, let's recall how we collect communication and I/O fragments. Communication and I/O fragments are actually external functions for Vapro. Their workload is well defined by their arguments. For example, for MPSN, we can collect the number of elements, the type of them, and their destination to describe workload. Now, we can fully describe workload for both computation, communication, and I/O. The next problem is how to identify fixed workload fragments according to their workload. To identify fixed workload fragment of communication and I/O is straightforward since it's directly described by their arguments. However, computation is different. PMU data has inherent error due to the hardware design. In the previously shown example, although the total number of instructions looks stable, if we zoom in on the axis, we can find that there is a small variance. To solve this problem, Vapro clusters workload metrics to identify computation fixed workload fragments. For easy to read, Vapro reports the relative performance of applications to user. The collected execution time is normalized to their relative performance, which means the fixed workload fragments with shortest time is normalized to relative performance 1, and fragments with longer time are normalized to smaller performance ranging between 0 and 1. For example, in this case, there are two sets of fixed workload fragments. To normalize them into relative performance, we find the shortest time in the fixed workload fragments respectively, which are 10 milliseconds and 27 milliseconds. And other fragments are normalized according to them. At last, Vapro reports performance of a period, which is the weighted average of all fixed workload fragments in the period. We use execution time as weight for each fragment. Now, let's come to the diagnosis of variance. One challenge is that there are too many performance data and it's infeasible to monitor all of them at the same time. For example, there are hundreds of CPU PMU metrics and also extra software performance metrics. To diagnose variance, our idea is based on dividing variance into several factors. For example, we can at least divide the execution time caused by variance into three factors. That's computation, communication, and I/O, since Vapro collects them separately. Next, the question is that can we divide them into more detailed factors, such as specified events in a CPU or an OS? For example, computation can be divided into CPU, memory access, and operating system influence. and we may want to a more fine-grained breakdown. For identifying performance issues in CPU microarchitecture, we focus on PMUs at first. An interesting finding is that there is a similar structure in PMU. This figure shows the top-down microarchitecture analysis method, or TMA for short. It is used for identifying performance bottleneck in the microarchitecture. TMA organizes functional blocks of pipeline into a tree hierarchy, and it enables cycle counting for functional blocks, which means we can calculate how long a block costs. For example, the time of front-end bound can be calculated by this expression for Intel Ivy Bridge CPUs. Based on this design, we can break execution time down. Then, the question is that, can we break down variance as well? In fact, the difference between the execution time of normal fragments and slow fragments is the time of variance. For example, for slow and normal fragments, their time is broken down into 4 factors. The difference of them shows that the slow fragment spends 1 more second on backend. Thus, we know that the variance is caused by backend, and we can deal with metrics in TMA since all of them can be quantified in time. And the immediate question is how to deal with other metrics outside of TMA metrics. To solve this problem, we propose the variance breakdown model. It supports both hardware factors and software factors for computation. The left part shows possible factors when program is running on CPUs, and the right part reasons when process is suspended. A challenge here is many software factors are not quantified in time. For example, Linux provides the count of page faults instead of the time they cost. At present, we have a great number of fixed workload fragments. We have their execution time, their performance counters, and the fragments have same workload. Based on this data, we can use a statistical method to estimate the time of each factor. If we assume each metric has a linear impact on execution time, we have the following regression expression. In this expression, beta I is the impact of a single unit of fact j on execution time. By performing a regression on fixed workload fragments, we can estimate all betas in this expression. Thus, we can quantify variance for each factor. Now, after quantifying the time of each factor, we come to the diagnosis algorithm. As we can see in this figure, variance is inclusive in the performance breakdown model, which means the time of high-level factor includes the time of the low-level factors. So, we can diagnose performance variance stage by stage. At first, Vapro locates a coarse-grained factor and drills down the hierarchy. This method keeps a small number of collected performance data, and it introduces relatively small overhead. Now, I'm going to show the evaluating results. We conduct MPI experiments on Tianhe 2A supercomputer and OpenMP evaluation on local cluster. We evaluate our approach with 18 programs, including complex programs such as CSM. We evaluate Vapro against vSensor. vSensor is our baseline in our evaluation, and it's a variance detection tool that can find fixed workload code snips with compiler analysis. Since it's based on static analysis, it cannot be applied to many circumstances in the production environments, since we have no source code of applications, and it cannot do the diagnosis as well. Here is the basic results. The overhead of Vapro on MPI applications is 1.8% and 1% for OpenMP applications. As we can see, the overhead of Vapro is 0.8% higher than vSensor. Since vSensor is a static analysis-based tool, it has lower overhead. And we can see 1.8% is a tolerable overhead in most circumstances. Next, another important metric is detected coverage. This metric shows how much time is covered by fixed workload fragments. A higher coverage covers more execution time, and more variance is likely to be found. The results show that Vapro has a 75% average coverage and is 30% higher than vSensor. This shows the average detection ability of Vapro is stronger than vSensor. The final detection results look like this. We use color scale to represent relative performance. The darker color means higher performance, and the white color means low performance. The vertical axis is the process ID, which indicates where the performance variance is. The horizontal axis is the time progress, which tells us when the performance variance occurs and how long it lasts for. At runtime, our tool will calculate the relative performance for each process at each time slice. In this result, performance variance will be represented by white blocks. Users do not need to investigate tons of logs. They only need to find out light color blocks in this figure. We will see more results in the experiments. In this case study, we run HPL on Intel processors. HPL is the benchmark used in the top 500 tests. It has stable performance and there are relatively little communication. In our evaluation, it has usually less than a 2% variation of execution time. However, we met an execution with 22% longer time. From the output of Vapro, we can see the bottom part has lighter blue color, which means process on the socket 1 is influenced by variance. To diagnose this variance, we focus on the report from Vapro. On this variance breakdown model, Vapro shows 96% of the variance is caused by back-end bound, and more than 86% of overall variance is from memory bound. At the last stage, it shows level 2 cache, and DRAM contributes about 40% of overall variance, respectively. This shows extra cache misses and memory impaired performance. To identify the underlying reason, we have more evaluations and found this variance matches a severe Intel processor hardware bug related to the level 2 cache. This hardware bug makes data in the level 2 cache frequently evicted and generates random but significant slowdown. To solve this problem, we use huge page to mitigate this problem. This figure shows the performance distribution of HPL on the 2 MB and 1 GB page size. The blue line shows with 1 GB page size, there is a smaller performance variance. It reduces standard derivations of execution time by 51.3%. In this case, Vapro not only makes an early stop for the affected programs possible, but also avoids time-consuming execution for diagnosing this non-deterministic problem. In this case, we focus on a memory problem. Vapro detects a variance for neckbound on Tianhe2A. The white block in the output shows that all processes on a node have lower performance. Vapro further diagnoses this variance and shows that 97% to % of variance are from back-end bound in CPU. To further locate this problem, we run memory bandwidth test, and it shows that this node has lower memory bandwidth than others. By replacing this node, we can have a 1.24 times speed up. In this case, we focus on an I/O problem. Vapro detects a variance for a parallel program on Tianhe2A. Its execution time is varied from 41 seconds to 68 seconds in 10 consecutive executions. Although Vapro reports computation and communication performance are normal, it shows that process 0 has lower I/O performance. Detailed collected data shows its read operations have significant variance on distributed file system. By adding a new simple file buffer, we have a 1.18 times speed up and a 73% reduction in the standard derivation of overall execution time. In conclusion, the most important idea I would like you to remember is that to diagnose performance variance without source code of applications, we propose two techniques. To deal with no source code, we use runtime workload identification to find fixed workload fragments. To realize diagnosis, we propose variance breakdown model to divide variance. Based on this idea, we present Vapro, a variance profiler. It can efficiently locate when, where, and why the variance happens, even without help of application source code. Some details are not discussed in this presentation, so please read our paper if you are interested in this work. Thank you, and questions are welcome.